So today we are going to do few problems from Gauss's law. So before we go to the actual problems, there are few concepts that I want you to know. I think that you already know this, but let's review it. So you all can remember this equation, right? Gauss's law. So this is your favorite equation, the Gauss's law. And we know about this side, right? So this side gives you the electric flux. That is what we mainly did last time. Finding electric flux. Electric flux through a closed surface. So what we mean by the closed surface is actually the Gaussian surface. What we draw as the Gaussian surface. Electric flux through the Gaussian surface. So the part right here is the charge inside your Gaussian surface. So it is all about the Gaussian surface, okay? So today we are going to look at this side of the equation. Why? Because you will see in Gauss's law, when we actually start applying, this is not the hard part. Electric flux part is not hard anymore. Getting this Q enclosed becomes hard. The reason is because you will have to get the charge inside a Gaussian surface. So most of the time you will see in questions that they have defined these quantities. They have given these quantities instead of at the actual charge. They usually give the charge density instead of the actual charge. So we have to know what these are and how to work with this. Okay. So the first one. So the first one has this symbol lambda. This is called the lambda. This is lambda. So lambda is the linear charge density. I'm pretty sure that you have seen this before. So when you have a line charge, so this charge is contained in this line. So let's say it is a uniformly charged line charge. It's like a wire. So this is something one-dimensional, right? There's only a length to this. So for a one-dimensional object, we define something called a linear charge density. So what is linear charge density? Linear charge density, lambda, is the charge per unit length. So it is the charge of a unit length. It is a density, right? So why do we only have a length? Because this object, a line, only has a length, right? It doesn't have any other dimensions. It doesn't have an area or a volume. It only has a length. So let's say this length is capital L. The total length of your wire is capital L and the total charge was capital Q. So if to get the charge per unit length, they divide the total charge by total length. That is how they get the charge density. See, total charge divided by total length. That is how you calculate a density, right? Okay. So with this equation in mind and the definition of lambda, lambda is the charge per unit length. Can you tell me charge in L over 3 length? Can you tell me what that is in terms of lambda? In terms of lambda, can you give me the value of charge in L over 3? How can you calculate it? Let's say charge is Q1 for now. So we know the charge per unit length. So what is the charge per L over 3 length? Lambda times L over 3, right? So it's something like this. Let's say price of a mango, $1. Price of 5 mangoes. What would you do? You will multiply price of 1 by the number, right? So the same thing. This is charge per unit length. So you multiply charge per unit length by your length. So this will give you the charge of this small length. So this mango story, can you tell me price of half a mango? No, 1 over 3 mangoes. What would you do? Yeah, so you will multiply 1. 1 is price of one single mango by 1 over 3, right? So the same thing. Price of charge of one charge per unit length. You multiply the density by the length. So you get the total charge in this small part. So let's say this is your L over 3. So you get the charge in this part. Okay. So in the same way, there are quantities, there are other densities that they have defined for other dimensions. For example, something like a sheet charge. You know sheets, right? Sheet. Something like a sheet. So a sheet has an area, right? It not only has a length, it has a width. So this has an area. Therefore, two objects like this, which are two-dimensional, they have defined something called sigma. Sigma is the surface charge density. So just like linear charge density, this is called the surface charge density. In other words, it is the charge per unit what? Area. Okay. So if I ask you to find the charge of 2 square meters, how can you find it? Just like this one. You will be multiplying the surface charge density by the area you are interested in, right? So same thing happens all the time. Here you multiply lambda, the density, by the length you are interested in. Here you are multiplying your density by the area you are interested in. So in the same way, we can define something called the volume charge density. For a volume, there are solid objects, right? So for solid objects, line charge density or the surface charge density does not make any sense because it has a volume. So volume charge density, this symbol is called the rho. Rho, I don't know how to spell it. You pronounce it as rho. It is defined by total charge over the volume. So you define volume charge density for volumes or three-dimensional objects. So rho is the charge per unit watt. volume. So if you need to find the volume charge of let's say this tiny sphere inside this main sphere. Let's say this has an area of simple A. How to find it? Charge of the small sphere with area with radius A. So I know you all know how to do this, but you all are not sure the volume of a sphere. So I want you to tell me the formula for the volume of a sphere in the chat. Tell me that. Ooh, yeah, good. So I got many correct answers. So the volume of a sphere, so that's why you all are getting higher marks than the other class. So volume of a sphere is 4/3 pi r to the power 3. Area of a sphere. What is the area? You don't need it for this problem, but I got 3 different types of answers. Let's see. What is the right one? So the correct answer is yes, 4 pi r square. So these are spheres, not circles, okay? So for spheres, you always have this 4, okay? In volume, you need to have power of 3, right? Because the unit should be cubic meters. Because volume is 3 dimensions. So you need to have 3 quantities multiplying with each other. So that's why you have 3 here. Here you have 2 because this is an area. So this you have to remember because for the exam, they will not give you the areas or the volumes. So I have seen in years that you all know how to do the problem. You are okay with physics, Gaussian, everything. You know everything. You forget this and you get 0. Okay, so you need to know this. So cylinder, sphere, spherical shell. Learn about the areas and volumes of those. Cylinder, sphere, spherical shell. Okay, so here you are going to multiply by 4/3 pi a cubed. Okay. So here, before doing the problem, just do part A and tell me the answer. So volume charge density means, so here I am asking you to calculate rho. Rho is total charge Q divided by the total volume. So it is a sphere, therefore 4/3 pi capital R cubed. Why capital R? Because this sphere, the radius of the sphere is capital R. Okay, this is the answer for the part 1. So sometimes in problems, they will give you the value of rho. They will just ask you to calculate your answers, do the problem using rho. But here in this problem, they have given everything in terms of Q and R. So your final answer should be left with Q and R. So let's see how we do B and C. So before doing B and C, I'm going to rewrite Gauss's law. So this is how you have it in your lectures. And there are a lot of other ways that people write this. So I will stick to what we did last time. EA cosine theta. Can you remember in a sphere? In a sphere, what happened to this theta? In a spherical Gaussian surface, what happened to this theta? We talked about this last time. What was the value of theta? So I got one answer which was correct. Anyone else? So very good. So cosine theta goes to 1. That means the value of theta is 0. Do you want me to show you how that happens? Or are you okay with that? If anyone wants me to show that, I can show you how it becomes 0. Show it, please. Yes, I can show it. So for a spherical object, the Gaussian surface is also a sphere, right? Are you okay with that? So if your object is a sphere, your Gaussian surface is also a sphere. We like to make it symmetric all the time, right? Remember? So let's say that you have some charge in this, and this is your Gaussian surface. So this is not part B or C. This is in general, okay? So a general part. So what can you tell about the electric field lines which go out of this sphere? Let's say this is a positively charged sphere. We know electric field lines are always perpendicular to the surface. Am I correct? Yes. So electric field lines are always perpendicular to the surface. So these are my electric field lines and they are perpendicular to the surface. So they are perpendicular even to the Gaussian surface, right? Because it's also a sphere. And what is theta? What is this theta? Theta is the angle between electric field and n hat. What was n hat? What is n hat? N hat is the perpendicular drawn to the surface, right? Very good. So perpendicular drawn to the surface. So here is here are the perpendiculars drawn to the surface. So what can you tell about E and n hat? They are along the same direction, right? E and n hat are along the same direction. That means theta is 0. The angle between n hat and E is 0. They are along the same direction. That is why theta is 0 and it makes the value of cosine theta go to 1. So I'm going to do the problem. So my first step is, so look carefully at each step I do. Okay. So this is my spherical solid insulating sphere and it has a charge Q. So in a insulating sphere, what can you say about the charge distribution? What do they mean by uniformly distributed? Is it distributed from the center to the surface equally, or it only has charge in the surface? Very good. So it is evenly distributed. It is throughout the sphere. So whenever you see insulating, that means throughout the sphere, this charge is spread evenly. Okay, yeah, good. So the next part is part B. They are asking us to find the electric field inside the sphere. Okay, we are going to find the electric field inside the sphere. So I'm going to use a different color. So they're asking us to find the electric field somewhere here, right? Which is inside the sphere. So my R1 is smaller than capital R. Step 1. You have to draw the Gaussian surface. This Gaussian surface is the most important thing. So this is my Gaussian surface. Gaussian surface is an imaginary symmetrical surface. In other words, it's another sphere that you draw at the location you want to find the electric field. So you want to find the electric field at a location like this, right? Inside the sphere at R1. So here I drew a Gaussian surface. So are you okay with the location I drew the Gaussian surface? Yes? Okay. Step 2. Step 2 is doing this part of the equation. So I'll call left hand side of the equation. Now let's figure out what's happening in the left hand side. So we are going to find the electric field, right? So I just write E. And what is this A? What is that area? Area of what? Area of the sphere. Which sphere? Is it the Gaussian sphere or the big sphere, the one in red? So I got one answer. Yes, Gaussian sphere, GS, Gaussian. So it's not the big sphere. Okay. So it is the Gaussian sphere. Why? Because I said this equation is all about Gaussian surface or Gaussian sphere. That is why this equation is called the Gauss's law. So we draw imaginary surface. Why? Because we need to find the electric field here. So I got a question in the chat. Why not the entire sphere if it is uniform? So we are going to find the electric field at a location like this, right? We need the electric field inside the sphere. And our Gauss, that means our Gaussian sphere should be inside the sphere. And this area is the area of the Gaussian sphere. So if I go to the previous slide, can you see I wrote this is the electric flux through the Gaussian surface. See, this is the electric flux through the Gaussian surface. This is the charge inside the Gaussian surface. So this whole equation is about the Gaussian surface. Okay, that is why it is the Gauss's law. So are we good? So E, and just like you all said, we have to get the area of the Gaussian sphere. This one. So it is 4 pi R1 squared. So this is the area of a sphere, right? Area of Gaussian sphere or the Gaussian surface. So we are done with step 2. Now we go to the third part. We have to do the right hand side, but before that we have to know what the enclosed charge is. This part. In other words, we have to figure out the right hand side of the equation. So what is Q enclosed? What does that mean? It is the charge inside the Very good. Charge inside the Gaussian surface. Charge inside the Gauss area enclosed. Very good. So that means you have to look at the charge inside your Gaussian surface. So that now that is hard, right? How to get that? You all know that already. Can you tell me how can we calculate enclosed charge? Yes, we use rho. We know the value of rho. And what after that? We multiply rho by, very good, rho by the volume. So we have to multiply rho by the volume of the Gaussian surface. Here, why Gaussian surface? Because all the charge we need is inside the Gaussian surface, right? So here we multiply it by the Gaussian surface. So this charge. So what do we get? Rho is given by Q over 4 over 3 pi r cubed. This rho, right? From here. And what is the volume of your Gaussian? It is 4 over 3 pi R1 cubed. So we can simplify this a little bit. 4 over 3 pi get cancelled and we are left with pi r cubed into R1 cubed. So are you okay with the charge enclosed? So that is the hard part in this problem, in the Gauss's equation. So in the step 4, we write the whole equation. My left hand side is E 4 pi R1 squared. Okay, this one. It is equal to Q enclosed. We just found it. Q R1 cubed capital R to the power 3, and you have this epsilon naught, right? In the denominator. Okay, so what do we get when we simplify this? You can simplify it and tell me. Tell me the value you get for E. So you have got so this is what you have got. I'm writing what you are sending me through the chat. You got 3R1 divided by 4 pi. That's the 4 pi epsilon naught R to the power 3. So is this what you got? Yes. So again, now we are going to do an important part. What can you say about these terms, which I'm circling? Q 4 pi epsilon naught capital R. What can you say about those? Are they constants for the problem? Yes, right. Capital R won't change. It is the radius of your object. Q is the charge of the object. So all of these terms are constants, right? So we can see that E varies with or changes with R1. So When R1 is what? R1 is the distance from the center to some location inside your sphere, right? So R1 is inside your sphere. So when when R1 is 0, what is your electric field? Can you put 0 to the equation and see what will happen? Electric field is also 0, right? If R1 was 0, if this was 0, this is also 0. When R1 increases, E is also going to increase. So if I drive this, so this is very important because in problems, in multiple choice problems, they like to test this very often. Variation of the electric field with the radius. So can you see that it starts from 0 and increases till capital R, till the radius. Like when it goes this way, the electric field increases. Why? Because the enclosed charge is increasing, right? When your Gaussian surface goes from this tiny one to a bigger one, you can see enclosed charge increases, right? So even by looking at this equation, you can see that electric field increases with the radius till the maximum radius, till R. So we will look at this side when you go to the next part of the problem. Okay. So here, so I'll do part B with this problem. And now I want you to tell me about the distribution of charges in a conducting sphere. Very good. So is it on the surface or it is evenly distributed inside also? So it is surface, right? So in a conducting sphere, usually charges are at the surface. Can someone tell me why? So for part C in the last problem, so we will do part C when together with part B of this, okay? So can someone tell me why this happens? Very good, like charges repel. So that is the main reason. So this is a conductor, right? This is a conductor. Conductor means what? Let's say you give it some charges. Charges can move through a conductor, right? So when it is charged, can these charges stay like this? No, right? They repel each other. So they repel each other so that they will go far away from each other as much as possible. So they will eventually be like this. So this is the most stable way that charge can exist because this is a conductor. Charges can move. So if they can move, they will move, right? If they're repelling. But in an insulator, moving is not a choice. Because charges cannot move inside insulator, it stays as it is. So can you tell me the electric field inside a conductor? Zero. So you are good. So electric field inside so this is something that you have to know. Whatever the shape you have, whatever the Gaussian, whatever the object you have, whether it's a cylinder, whether it's a sphere, whether it's a shell, always inside, so this is important, inside conducting material. So I'm not talking about hollow stuff, okay? So this is not about hollow stuff, not hollow. Inside material, inside conducting material, the electric field is always zero. For example, let's say we had a shell, okay? Let's say we had the conducting shell. Shell means you have conducting material here, right? You have conducting material here. Inside is empty. There's nothing inside, right? So electric field will be definitely zero here, where the conducting material is available. But we don't know what's happening inside. There can be charges, there can be an electric field. So we don't know about inside. It will depend on the problem. But we definitely know inside conducting material, where there is material, electric field is zero. So a lot of people get confused with this and this. So we are not talking about this area. Okay, we don't know about hollow stuff. Okay. So E is zero. That is something that you have to remember. And if you are going to apply Gauss's law to get that, this is how we do it. This is your Gaussian surface, right? EA, your area is, so this is the Gauss's law, right? So your E is the electric field inside. A is the area of your Gaussian surface. Very similar to the previous case. And Q inside is zero. Why? All the charges are in the surface now. Divided by epsilon naught. So your E is zero, right? Now I want you to do part B. Can you try part B? So did you get this? So here, this is your Gaussian surface. E times the area of your Gaussian surface is equal to charge inside your Gaussian surface. What do you have? You just have the charge of this, right? So you have Q divided by epsilon naught. In in this side. So your answer is very similar to a point charge, right? The electric field distribution of a point charge. So this is the same thing that you would get for part C in the previous problem. Oops. So if we draw this, how would it be? Electric field till R, that means the radius of the object, your electric field is 0, right? Because in inside, you don't have electric field. Inside, you don't have electric field. And after R, it's going to reduce like this, right? In use like this, inverse law. So what about the previous problem? So this is the conducting solid sphere. In the previous problem we saw why isn't it drawing? Okay. It was like this till R, and then it is the same thing as this. Okay.
In your answer that you have circled, it's on the bottom, it's 4 pi epsilon naught R to
the power 2.
To the power 2.
So are you okay with these two diagrams? These are very important. So this is for a conducting, this is for a insulating. Here is a problem. I know it looks complicating, but it is not. So it is a combination of all the things that we learned up to now. And so I'll explain what is there in the question. So in the question, this small circle inside with a radius A, this is an insulating sphere with charge density rho. Okay, so it is very similar to the previous problem, the insulating problem we did, except that they have given the rho directly. So we have this insulating sphere with rho charge density, and right here from A to 2A, so this area, there's nothing. And here, this thing, it's a conducting shell with a small thickness, minor thickness. See, it is a conducting shell. And right here, right here, it is a insulating shell. They haven't even shown a thickness to that. And they say charge negative Q naught is distributed in this. So those are like, we have a solid sphere and two shells. So that's the question. So in part A, they are asking to find the electric field inside your small sphere, right? So I'll use a different color. So the radius of this is simple A, they have given in the question. And they are asking us to find the electric field of a location like this, which is inside. So this is very similar to the problem we did before. So the first step is drawing the Gaussian surface. Okay. So you have to tell me if each step is clear. If any of the steps are not clear, Just tell me. So I'm going step by step again. So the first step is to draw the Gaussian surface. Are we okay with that step? Are you okay with my Gaussian surface? Yes. So Gaussian surface. Second step is figure out the left hand side of the equation. So what is your equation? This, right? EA Q enclosed over epsilon naught. This is your Gaussian equation, Gaussian law for a sphere. So we are going to figure out this. So LHS is going to be E. That is what we are going to find. And A. What is the A? A is the area of your what? Gaussian surface, right? I said this whole equation is about Gaussian equation. Yeah. Gaussian surface. So it is 4 pi. They have used R1 squared. So that is the radius. So we are done with the second part. Third part is figuring out this side. That is finding the enclosed charged. So how to find the enclosed charge? Enclosed charge is what is inside this Gaussian sphere. So how to find it? They have directly given us rho, right? So we use rho. They have given it in the question. Rho times the volume, right? So what is the volume of your Gaussian sphere? 4 over 3 pi R1 cubed. So are you okay with second and the third steps? So you know how each and every term came, right? How we got this. This is the volume. So now it's just a matter of equating left hand side and right hand side. So my left hand side is 4 pi R1 squared, and my right hand side is rho 4 over 3 pi R1 to the power 3. 4 pi get cancelled. See, 4 pi get cancelled. You get E rho over 3 R1 cubed divided by R1 squared. So this get simplified further, right? So your electric field is rho over 3 R1. So rho is a constant, 3 is a constant, similar to what we saw before. So in this problem, there is I'm sorry, epsilon, no. Sorry. So this is Q enclosed only, right? So you need to have epsilon naught. Sorry, I forgot that. So whole thing divided by epsilon naught. So you get epsilon naught. Epsilon. Okay, sorry. So are you okay with this? So here you don't need this, but if I draw it, electric field increases with the radius till A. So same thing what we got before. Here we have constants. R1 is the variable. With R1, electric field increases. So you're good with part A, right? So when we go to the next part, you will see we are repeating every step over and over again. Oh, you want me to go back? Tell me when you are done with this. I will move to the next one. Done? Not done? No answers? You've started hating me already. Okay. It's okay to hate me. I made the last quiz hard. So R2. At R2 is somewhere in between your insulator and the conductor, right? So somewhere here. So I usually like to draw each object separately. So for R2, only what's inside matters, right? So I usually like to draw it like this because it makes the problem less complicating. So this is your R2. The radius is A. Okay, now you all are going to tell me the steps. Tell me the steps. What is the first step? What do we do? Very good, Gaussian surface. So I'm going to ask you to tell me what to do. Okay, Gaussian surface. Second step. Left hand side. What is the left hand side? EA, right? So we have to figure out what EA is. What is EA? E is the electric field. A is the area of your Gaussian sphere. So Gaussian sphere is 4 pi R2 squared. Third step. So this happens quickly. That is good. So right hand side. Specifically, we need to figure out the Q enclosed, right? So what is Q enclosed in this one? So in this problem, they haven't really given us Q, right? They have just given us row of this thing. So how can we get Q from the row that they have given? Rho times volume. What is the volume you have to use? You have to use the volume of this, right? Yeah, it is the entire volume. Entire means the volume of this object because charge is only in this thing, right? There's no charge here. There are no charges here. So your Q enclosed is the charge of this insulating sphere, which is rho times the volume of your insulating sphere. So volume of the insulating sphere is 4 over 3 pi A cubed. So are you okay with this? So this is the important step in this. So are you okay with this part? Why I multiplied by 4 over 3 pi A cubed? That is because we only have charge inside this, right? So what we just did was we calculated Q of this. Okay, now we have done most of the steps. Now we just have to put all of this into the equation. So the equation is EA Q enclosed over epsilon naught. EA is E times 4 pi R2 squared. And this side, it is 4 over 3 pi A cubed inside the bracket divided by epsilon naught. So now we have to write it nicely. 4 pi get cancelled, right? In both sides. So I'll write it directly. Rho 4 pi got cancelled. You are left with a to the power 3 here, or sorry, 3 from here, epsilon naught, r2 to the power 2. Can you explain why you use a again, not r2? So here I used a because we wanted to find the charge inside our Gaussian surface, right? So what is the charge inside our Gaussian surface? Just this, right? So what we had to do was get the charge inside this insulator. That's the only place where we have charge. So how to get the charge in this? You multiply rho by the volume of this. So what do you mean by surface? What about the charges on the surface? So when you multiply by the volume, so A is the radius of this. So it all captures into this. So this is a Gaussian surface which is imaginary. There are no charges on the Gaussian surface. So another question, how do we know when we are supposed to solve rho? Like in the first problem. So in the first problem that I did initially, they haven't given you rho, right? They didn't give you rho, but however, you had to calculate charge of a part of your insulator, right? Not the whole insulator. So in instances like that, you have to. But in problems like this, they have directly given you rho. When they directly give you rho, you don't have to calculate. So at R3, what happens? What is R3? It is inside the conductor. Can you see it? So that is the most important thing. Inside the conductor. What is your electric field? 0. But you must have, like, if you try to calculate it using Gauss's law, did anyone find it confusing? Did anyone find getting E equals 0 hard when you just use Gauss's law? Anyone? So I can explain you what is happening if you want to go like in that direction. I can explain you how you can get equal 0 even using Gauss's law. Tell me in the chat if you need it. So if this was a long answer question on the test, could we just write 0? I think you can just write 0. So in this exam, they just gave marks for equal 0 because you can write inside a conductor, E field is 0. With that reason, if you write it, you would have gotten full marks. So if you got few yeses for the previous question privately, so if you just use Gauss's law, so your Gaussian surface is something like this, right? So I'm going to not do it completely. I'm just going to show it what happens. Show you what happens. So this is your Gaussian surface, right? So E, this is your R3. Area is 4 pi R3 to the power 2. So the problem occurs when you look at Q enclosed. So what are the charges enclosed inside your Gaussian sphere? So that is the confusing part. You might feel like, oh, it is not zero. There is charge. That's what you feel, right? Like when you look at that, you feel like there are charges inside. We definitely can see that this thing is there, right? Yes, this thing is there, but this is a conductor. So in a conductor, like we have already discussed, charges can flow. So will it just remain like that? So will it just remain like this if there's a positive thing here? No, right? So there's going to be some induction. You remember induction conduction? So charges are going to negative charges. You might even have seen this in the lecture. Negative charges are going to get induced in this side of the spherical shell. This is like, you don't have to put it in the calculation or anything. I'm just showing you what's actually happening. So negative charges are going to come to this side so that it can cancel off this positive charge. So let's say this one was positive Q. Let's say this value was positive Q. So the total charge in this surface will be, the inside surface will be negative Q, just to cancel it off. So the total charge in your inside your Gaussian shell will be still zero. So that is what's happening when this shell is a conductor. Okay. So that is how your electric field will be zero inside a conductor. You don't have to know how it happens. You just have to know that electric field inside a conductor, no matter what the situation is always zero. Something will happen to make it zero. Induction can happen, things will happen so that it will be zero. Are we okay with that? Yeah. So let's go to the next part. At R4. Let me check the time. So we have around 10 minutes. So R4 is here, right? So this is your Gaussian surface. So now you must see that all of these sums are very repetitive. You write the same term again and again. So your electric field is what is we are going to find. Area. Sorry, I got an emergency alert in my phone. E area is 4 pi R4 to the power 2. What is Q enclosed? Total charge inside this. So what is the total charge? You have charge of this and charge of the shell, right? So what was Q from before? I think Q was 4/3 pi A cubed, right? So this Q, the Q here was that, and this is Q naught. So your total charge will be the charge of your insulating sphere, the dark blue one, which is rho 4/3 pi A to the power 3, and you have to add the charge of your sphere, right? Shell, right? That they have given it given as Q naught divided by epsilon naught. So, sorry. So this term, this is one term, this is the other term. Rho This is one term. Okay. So your electric field will be rho 4 over 3 pi a to the power 3 plus q naught divided by 4 pi epsilon naught r4 to the power 2. I know the expression looks complicating, but what happened is simple, right? You just find the total charge inside and then you divide it by 4 pi epsilon naught times radius to the power 2. Okay, last part. R5. R5 is here. So this is going to be your Gaussian surface. This whole thing. Don't mind my circle. It should be a sphere. So for EA, Q enclosed over epsilon naught, right? So can you see we are repeating the same things again and again? E is E. That is what we are going to find. A is the area of your Gaussian sphere, which is 4 pi R5 to the power 2. What is Q enclosed? So it is going to be rho 4 over 3 pi a cube. So this is from the insulating sphere, this one. And what else do we have? We have this shell and this other thing also here, right? So you have positive Q naught and a negative Q naught. So these get cancelled, right? So your electric field is rho 4 over 3 pi a cubed divided by 4 pi epsilon naught r5 to the power 2. So Q, what happened was Q naught and Q naught got cancelled because these two shells have opposite charges. So are we good? Yes. So this is one of the hardest examples that they can give you from spheres.